Hello and welcome to Module 1. And the topic we'll be talking about today is artificial neural networks, part of machine learning. They're probably, I should have started off with kind of an overview of what is machine learning versus what is AI. And there is some dispute as to what it is. From my perspective as an AI person, I view machine learning as a subcategory of AI because AI is tasked with the concept of understanding and acting in a way that resembles intelligent. In that regard, this course being around machine learning focuses on several topics that relate to AI, but more applied AI. And that's kind of the distinction I typically make, is that there's some aspects of AI that are, while they're applied, they're not as practical as some, and machine learning algorithms are very practical. So we start off with the concept of a neural network. You'll often hear the word artificial in front of neural network. We kind of all know inside of AI that we're not really dealing with neurons here. We're dealing with something that approximates a neuron or is based upon the concept of a neuron at the time that they were created. Now, there's a lot of differences as we've learned more about how the brain works and so on between what is reality and what we model, but the concept is kind of there. We're trying to emulate something like that. So at the end of the experience, you should be able to talk about things like neurons, nodes, layers, be able to talk about how neural networks learn, and to some extent talk about back propagation and things like gradient descent. So we'll talk about backprop a little bit more in the next module as well, but it's basically a way of kind of adjusting your weights as you're going through. So I fought off the urge of putting a zombie picture here, right, because brains, right? But anyway, the basic idea of an artificial neural network started with what we believe to be the understanding of a neural network or of a neuron at the time that this concept sort of started. It was off a bit, it's simplistic at best, but the idea though is to approximate something that is a small unit that makes essentially a very small decision and then shares that decision with other elements within a network. It isn't a true network in the sense of things being connected and things flowing from a source to a destination. So the basic idea of it all started with this McCulloch-Pitts unit, basically an artificial neuron. The basic idea is that you're applying a function to some inputs and producing some outputs. And the way to think about this, and the whole point of a neural network, is to simplistically think of it as approximating a really complex function. And you do that by essentially adjusting some weights, which we also refer to as bias, inside of each individual neuron. So there's a certain amount of weights that are adjusted through the process, generally, of backpropagation. Also, you have this concept of an input function where you're basically going to likely sum, in some simple way, sum up the inputs that you're receiving. There's an activation function that determines what you do, you being a neuron inside of a network. Simplistically, it's binary, it's on or it's off, but a lot of times you'll see a sigmoid function. We'll talk about those in a little bit more, but the basic idea then is to produce some output, and that output goes to some links. This is really simple compared to how the neurons truly work, but it works pretty well, and it's worked really well with the advent of some additional technologies along the way. And the top bit there is basically the summation with the weights being applied to the inputs and then summed up and then going through essentially some form of a function that determines what the output should be, is basically what I just talked through. It's math, so feel free to dig into it more if you want, but that's the basic idea. So early on, it was about how we thought the brain worked, and you have these inputs, you have some weights, you do some summation across the multiplication, essentially, of the weights and the inputs, and then you have an activation function that determines what to do, and then it basically produces some output. So generally speaking, we take that concept and we apply it in 3 different layers at least. There's an input, a hidden, and an output. We'll talk about that again more in the next unit. And as a bit of a heads up, I'm going to go a little deep on this first lecture beyond kind of what's necessary really for the assignments. I'm going to show you some code. We're going to potentially, if there's time, talk through backprop and an algorithm that does it, an implementation of it. But that's the basic idea here, is to kind of go over the concept first, and you'll write a paper in your first assignment. But I'm laying the groundwork for you to understand the code that you'll need to use later on. Deep neural networks, nothing more than there's more than one hidden layer. That's all that means. And that's a big deal because way back when dinosaurs roamed the world and you had to go to a library to do research, and I was getting my master's, we were very limited in what we could do with the processing of various levels and layers within a neural network. So we kept it relatively shallow, basically to 3. There were even cases where it was less than 3. But with the advent of both more powerful computers, things like GPUs to do a lot of this matrix manipulation, which is what this turns out to be at the end of the day, and some algorithms that were made it really smart to know how to consider these multiple layers, then we started really getting some advances. So again, the key concepts: you have neurons or nodes. These are elements that are connected together. They're the circles in this network. You have a collection of them that are essentially at the same depth from the input, and then they essentially are connected to things that are the next layer in the network, and there's cardinality within each of these layers. This is the 3-4-2 network is what you're looking at, and like a lot of things in this field, there's no magic way of doing this. A lot of times it's experimentation. You figure out how many layers you need and how many nodes you need at each layer based upon experimentation. And the number of layers, just as I'm kind of going through, it really depends upon the complexity of the problem, and you figure it out. You don't know it from the beginning. There's not some empirical rule that says, oh, I'm doing this, so I want this many layers. But as over time, you'll kind of get a sense of that. And the number of neurons in general is going to be a product of the number of layers, the number of nodes in each layer, and so on. So it's math. Again, this concept of a weight and bias. Weights are what helps you convert your inputs to your outputs. Oftentimes we start off with essentially random weights, and then we adjust them over time to be more precise as we go through the process. So it is something to experiment and learn. And the bias are used to adjust the output. So sometimes it is bias and weights, sometimes it's just weights. A lot of times we flippantly will just talk about weights because it's kind of the same thing. Then you have the summation function, sum of the weights times the inputs plus the bias to essentially shift it up or down, and that produces your output. A key concept to understand with any kind of connectionist approach like this is that you're gonna need a labeled data set. So it's supervised learning. You know what something is. You're basically taking some input. You're training the system to hopefully approximate that input so that it can then essentially fit the curve, right? And the curve in whatever dimensional space we're talking about. And so the basic idea here is you train on the data you see. You hold back a certain portion of it. And actually, in this case, we get into those 2 different sets of data. You have a validation set and a test set, the validation set being used during training to kind of get a sense of how well you're doing. Then when it's all said and done, then you use your test set. You basically will adjust those weights to reduce your error. And the idea is to get close to it, but like everything else, there's this concept of doing too much, and you'll essentially overfit it, which basically means that you'll do really great on your test or your training data, but when you throw something to the system that it hasn't seen before, it doesn't generalize well. So you don't want to overtrain. Unsupervised learning is the case whenever we don't necessarily know the labels, right? And we've talked about this in the past. So the basic idea here is that you get some inputs and you do things like clustering and look for patterns. Less well suited to this, although there may be cases where it can be used with some variations of things like maybe reinforcement learning. You also hear the word epoch, fancy word. All it means is it went through all the data and updated all the weights one time. And so it is doing the feed forward and the back propagation of and essentially adjusting the weights through the entire training data set. And oftentimes at the end of an epoch, you'll take your validation set and determine accuracy. So generally, you're going to need lots of epochs depending upon the starting point and what you're doing. Activation function is simply converting inputs to outputs with a conditionality. There are multiple types. So here I've listed, I guess, 5. Linear, basically a straight line, sometimes with a slope. A unit step, it's either on or off. Basically, it's off until you hit some threshold, and then it turns on, or vice versa. Sigmoid, it's basically kind of similar concept except in steps, right? And then there's your hyperbolic tangent and a rectified linear unit. The use of which one of these depends upon the situation. Sigmoid has been around for quite a while and is quite popular. But they allow you to basically approximate different types of data. So sigmoid wouldn't make much sense if you're doing something that's essentially binary in nature. The first kind of class of these is the simple feed-forward network, right? So you basically, again, have this activation function, and the one on the left is simply a step function. It's off until it's on, and then the sigmoid is essentially like the name, it's a sine sort of motion, oftentimes more like steps than a smooth sine, but that's the same basic idea. And whenever you're adjusting the weights, it moves around that threshold. Whenever you're talking about the early on when I talked about McCulloch and Pitts, it could do a lot of stuff, but not everything, right? So and, or, and not. And then there were some challenges with a lot of these early algorithms with things like exclusive or. Anyway, so a simple feed-forward network basically is a parameterized family of a nonlinear function. So you essentially adjust the weights as it goes through. And that kind of takes us to the granddaddy of them all, which was the perceptron. And a single layer perceptron, basically there's no shared weights, and you essentially are moving things around and adjusting the steepness of that cliff as you're doing so. The perceptron was really good, except for it didn't do well with XOR. So you could do and or not, but not XOR. So exclusive OR was something it couldn't do. And this became an issue because there's certain situations where you need that sort of stuff. And this gives you a hint there on the citation, 1969. This is not new stuff. We've been doing it for quite a while. So whenever we talk about neural networks and especially deep learning, you'll sometimes encounter things that are computational graphs, and it's a way of representing operations, and it's about getting data from one state to another. You'll also do some work ahead of time a lot of times, just as we've done in other classes, where you have to do a transformation to get the values into something that are useful. There's this concept of a one-hot bit encoding, and I added bit so it's clear. You'll often hear one-hot encoding or just one-hot. And basically what that means is you've got a byte array that one bit is turned on based upon each of the categorical values, and this allows you to then treat them in a numeric fashion. You also have hidden networks and so on. So computational graphs is just a way of representing an operation or series of operations as a network, right? So we can essentially break down the composite pieces, and it helps us know how to do that computation. Computational graphs are often used, especially in the field of big data. And various other locations. They may go by a slightly different name. You may hear DAG or something, directed acyclic graph, but that is the basic idea. So they can be used to describe the various models. This is somewhat theoretical, but it basically is a way of representing some of these things. Being a graph, you have a node and an edge. An edge represents the essentially functional argument. Node with an incoming edge is a function of that edge's tail, and so on. So the basic idea here is just a way of representing things beyond simple pseudocode. Computational graph for a forward propagating network. Another way of looking at the same stuff we talked about before. You're basically summing up some of the various weights and of node values, inputs, and so on, with potential activation functions along the way. A convolutional neural network, we'll talk about this more in the next few classes. And this is really, again, a survey right now that I'm introducing all the various kind of fields that we're going to cover, at least here briefly. They basically have this concept of a kernel. And the idea is basically, think of it as like a sliding window going over a series of pixels. And that's where you're doing this concept of kerneling across a series of pixels, coming up with, in a controlled way. And the idea is to be able to figure out the relative location of various values. This first came to be in handwriting recognition quite a while back. And we've now moved on to this concept of tensors, which are essentially multidimensional arrays. Also you'll see GPUs that are oftentimes used to do tensor processing, and there's actually tensor processing units, which are specialized versions of that. So whenever you talk about a traditional three-layer network to a convolutional neural network, you'll see that it is very, it's like I kind of said, you've got windows on top of the values that allows you to think of it in terms of essentially a three-dimensional sort of representation. This is where whenever you start seeing things like people are running algorithms to recognize cats versus dogs, probably are using things like convolutional neural networks. Recurrent neural networks, it's the basic idea here is that in that computational graph that we talked about briefly, you can have essentially cycles. So that's where the recurrent comes to be. They also have this concept of a state or a memory, and probably the most confusing acronym of all, short-term memory. So think about what that means for a little bit. But basically they have a way of remembering things for a certain amount of time with a degradation of that memory over time. Not that dissimilar to us people. And the basic idea is that it allows it to be more intelligent, and is also sometimes has things like video becomes an important element in these sort of things where there is a time factor. So kind of revisiting some of this, you've got this concept of network structure. So you have feed-forward networks, which is single and multi-layer perceptrons. These don't necessarily have state internally. Recurrent neural networks do have a certain amount of essentially paths that they go through and cycles and memory, and can do things like flip-flops and oscillation and so on. A computational graph for a recurrent neural network, and the key thing there is that it is essentially iterative in nature, where it can potentially be in a loop of sorts. And this is essentially showing the computational graph for a many-to-many sort of concept. And again, this is don't flip out on me on this this level of detail. We're going a little deep initially, and then we'll kind of rein it in as we go. So places where you use this stuff, vision, handwriting being one of the key ones, right? Because long ago, it was hard to get from a handwritten address, say postal code on an envelope, to getting it to a series of numbers. Now you'll notice almost every piece of mail you get will have a barcode code across the bottom with that information on it. I was looking to see if I happen to have an envelope here in front of me, and I don't. But back in the day, when people actually wrote letters and did addresses by hand and wrote out postal codes, it was prohibitive to have somebody sitting there reading those and typing them in, although that was what was done for a while. Eventually, some really bright people figured out how to do so with recurrent neural networks, and the world changed. And so it became basically a solved problem. That led us down additional paths, such as just generic handwriting, not just numbers, and then also moving into things like tracking, detecting people, motions, and various other things. Natural language processing is also going to be something that you do. Any of the home appliance sort of voice recognition software that's out there today using some form of this, and some of them are actually starting to do it on the edge. For quite a while, whenever you would actually do the wake up phrase and then issue your command to your device, it would actually send that command, that data out to a processor in the cloud, and you get back a response. It did so pretty quickly, so you didn't necessarily notice, but that's why a lot of devices don't work offline. People don't particularly like having some of their stuff that they're sending up to the cloud. And so that's also been driving that, coupled with moving that processing closer to people, to where that stuff is now being done on the edge. Reinforcement learning is a different sort of beast, and we didn't talk about it a lot here. But rather than telling something an answer that this is that, right? So this is a picture of a cat, this is a picture of a dog. Instead, reinforcement learning gives it a way of evaluating how well it did. And then through a mixture of experimentation and exploitation, the algorithm will utilize what it knows and then look for things it doesn't know to determine which is the right approaches to solving various problems. That's where IBM's DeepMind used it to play Go and win, which was something that was thought to be impossible. So jumping into some of the demos here. And again, I'm going to go into a smidge more detail than you need to worry about, so don't freak out. So this is, I have a tendency to ignore R, so I thought I would spend some time with R this time. So I'm installing a package here that's already been installed, fortunately, called Neural Net, and also Neural Net Tools. The basic idea here is that we want to approximate numbers being squared. So you input 1 and you get back 1, you input 2, you get back 4, you input 3, you get back 9. So that's what we're trying to approximate. Yes, it's a really simple function, but that's the thing that we're kind of doing here is neural networks essentially approximate functions. And I'm just making sure that I'm running these lines, make sure that everything's loaded up. So I've got the data here, which is the same that we just talked about. So the input is 1 is 1, 2 is 4, 3 is 9, 4 is 16, and 5 is 25, and so on. And then the next sort of step here to go through is essentially give that information to this algorithm. So we're saying do this approximation, telling it looks like that should be 10 hidden nodes, and we're giving it a threshold for the activation. And then we can take a look at what the model looks like. So the basic idea is the covariates and all this sort of good stuff. It gives us what the real function, and then so we can see how well it actually does whenever it's doing this. So we can actually plot what it looks like. Taking a moment. So again, here is your various sort of weights and so on, the results matrix and various other things. Looks like that's all it does. Okay, so whenever we actually plot it here, you can see those 10 hidden nodes. So we've got an input node 1, we got a bias coming in there, which is also internally. We've got some weights, then we've got another bias going into the output. And so then we can check and see how well it actually did. And with input, the expected values, the actual neural networks, and output values. And you can see it did pretty good. It's not 100%, but it's within pretty close. Most of those are rounding. They would round to the right value. So that's when you would call a success. And that's doing it with a relatively simple network. Not exactly sure that 10 is the perfect answer, although that very well could be, because we have essentially 9 sets that we're putting in, so each one of them is probably approximating it. But that's our first demo. So moving into the second one here, and this is imagine that you're a server and you want to be able to figure out in a restaurant if you're likely to get a tip or not, and what are those factors that influence you receiving a tip or not receiving a tip. So we have a value, customer will tip. We have a series of attributes which contribute to that, likely contribute to that outcome, right? So how good was the service? What's the ambience like? How good was the food? And so with that, we can basically construct. I'll bring in the libraries that we just made sure that are still loaded, and then we can read in the file restaurant tips, and then we can take a look at it here, and we can see the various values. So if the service is really high, and based upon and the ambience is and food is okay, then you may not tip, right? So it depends upon the factors of what's going into it, and some of those may or may not be easy to see. So we can go ahead and attach it, and then create a model here that has it looks like basically 5, and so we'll go through and make sure that's what it's doing, and a certain amount of a decay, and then we can run through and print the model out again and then actually plot it. And so again, we've got 5 nodes in the middle here hidden. There's 3 inputs, a bias, another bias that affects the output, and that's basically kind of one of the interesting ones here is this Garson is a way of presenting the factors inside of a neural network that are contributing the most, right? So it's a way of determining that in this case we can see that service is the thing that contributes the most to the outcome, followed by food, then followed by ambience. So kind of an interesting thing. The Garson might be something worth spending a little time taking a look at, if you're not familiar with it. And then our probably last demo is about concrete. And so the basic idea here is that the things that go into concrete determine how good it is. So you've how strong it is the other way to put it. So you've got cement, you've got slag, you've got ash, you've got water. Looks like superplastic, some coarse aggregate, some fine aggregate. And then other things that will contribute to the strength is the age and how much cement is in it, right? So those are factors that all kind of go into concrete. Some of us buy ours in a bag at our local hardware store, but if you were to make your own, you would definitely be using cement. The aggregates for sure, water, yeah, you definitely need that. I'm not sure about the plastic. But anyway, so plotting that neural network, we've got a whole bunch of inputs. In this case, we've got a single hidden layer, and then the output of being strength. And so we can basically figure out what the predictor looks like. And this one, it looks like is doing something a little more interesting of switching it over to 5 hidden layers and producing an output. So with that, I've talked a bit about the actual networks that you'll be seeing and using, right? So this is an early sort of introduction, and you don't need to know that to do the first deliverable, but you might find it interesting. So in your first deliverable, you're asked to explain the idea of an artificial neural network. So what is it? And then take a look at the rubric. So you're working as a data scientist at Reliable Dynamics, a robot development and manufacturing corporation. You work for Mr. Andrews, the CEO of R&D. He has to brief, looks like DARPA, on how neural networks emulate the human brain. The company's new line of autonomous robots that utilize this technology are being considered for purchase by the government, and your CEO needs to be up to speed on basically what it is and how they function. So you've been tasked with developing a working paper on the various components of artificial neural networks used by the company's robots. Your paper needs to explain how artificial neural networks function and provide an example. You also need to provide a definition of neurons, nodes, and layers, and explain how they are interrelated. Define and provide an example of the backpropagation process and the gradient descent iterative methodology used in machine learning. And then provide an in-depth coverage of all the above elements. Your working paper will be in the form of a Word document in APA format. So your rubric, and as always, shoot for that mastery column, number 4. A thorough and detailed discussion has been developed that explains how artificial neural networks function, and you have some examples, and it's well developed. A thorough and detailed discussion has been developed that provides a definition of neurons, nodes, and layers, along with an explanation of how they are interrelated. And a thorough and detailed discussion has been developed that defines and provides more than one example of backprop and gradient descent iterative methodology that is used in machine learning. So we are pretty much at the end of this session. I'll briefly show this just because I can. But the basic idea here is I took a look at this and found essentially a description of working through backprop and with Python and NumPy. And this whole thing started back from an article published on MSDN back in 2017. And the idea is to show how to use this sort of approach in Python and NumPy so that you have a better understanding of what's going on whenever you're using things like CNTK and TensorFlow. So the idea here is to use Iris, our good friend, as the data set that we're working through, and to walk through the concept of how backprop actually works. And so you can download this from GitHub on looks like githubs.com/Lee-Stott /iris/blob/master/nn_backprop.py. I basically took that, made it pretty, split it up so we can actually step through it. So the first step, as always, is to make sure that NumPy, random, and various relied libraries are loaded. Then we have a series of functions that are used, and these are all helper functions. Load a file, be able to show a vector, show a matrix, show part of a matrix, and then, so I'll go ahead and run those so that they're available. And then this being a pretty well written code, uses a class to represent a neural network. So you have an init function that has a number of inputs, a number of hidden layers, and a number of outputs, and then a random number seed to help you potentially making sure that it's reproducible if it's so desired. And that's what we're doing right here, is making it towards reproducible. And this is doing nothing more in the init other than basically saving those values as essentially class variables. The next step is to go through and set the weights. These are the weights that are used by the various nodes. And then the corresponding get weights, initialize weights, which is likely going to set it to a random value between -1 and -0.01 and 0.01. So pretty narrow range there, but within that range being random. And then here we compute the outputs. There's a training operation that goes through and actually does the train, calculates the accuracy, so how well did it do, and probably, and also then computes the mean squared error. Doesn't look like that's being used necessarily in the accuracy, but it calculates it, comes up with the hypertangent. Likely that's our activation function. You got softmax and then the total weights. Go ahead and run that cell to create the class. So we start off, in this case it's just letting us know what version of Python we're using and what version of NumPy. Don't figure it matters too terribly much. So we're going to create a 453, so 4 inputs, 5 hidden, and 3 outputs. 4 likely being because it's the number of classes in the iris, although there's 3 in iris. I'm not sure why there's 4. Anyway, maybe it's if there's something that's not terribly clear. Then we load the iris training data into a data frame and convert it, the trained data matrix, from the trained data frame into a NumPy matrix. And this is our training and test data. Then we're going to let this thing run for 50 epochs with a learn rate of 0.05. And that's another thing to consider with anytime you're training neural networks, is they run for generally a certain amount of time. Long running stuff, you actually will typically let them run. They generate at each epoch, they generate essentially a checkpoint, so that you can then take that and determine the accuracy based upon the validation set to determine if you want to stop it or keep it running. And the idea is you're kind of balancing essentially loss with accuracy. And again, you don't necessarily want to overtrain. All right, so I didn't create my NN somewhere here. I didn't run that. Here we go. So here we ran through 50 epochs. It only prints out at the end of every 10 epochs, giving us an error at each time. So if you want to see overfitting, and this is the basic idea of why more is not always better, we can do the run here and basically figure out how well it does whenever you're doing too many. And so we'll go ahead and run through this. This is talking about how you calculate mean squared error, and that R squared is the normalized version of the mean squared error, not necessarily R squared. And then we basically can run through some of these various, and what I'm basically doing here is running from 1 to 100 different epochs. So this would take quite a while if I let it finish. But trust me that there's a reason why the author originally chose 50, right? Whenever they picked that 50 is how many it should run, that's because if you go much over 50, you start overfitting and you actually get worse results. So the takeaway from all that is that more is not better. And here you can actually see from a previous run that the epoch error ends up, and the test accuracy is a better one to look at, ends up doing much worse over time. So the basic idea here is don't overtrain. So find the level that works. And a visual representation of that is that around 50 is kind of that place where the epoch error is essentially minimized and test and train accuracies are maximized. So probably part of why that was selected as the value. And with that, I'll go ahead and shift back here. As always, if you have any questions, let me know. That's what I'm here for. Hopefully this was helpful. Hopefully it prepared you to at least kind of get hit the ground running and start working on that first deliverable. If you have questions, let me know, and we'll talk again next week.